So this is Jeff Hamrick at Rhodes College, and I'm going to talk about using a randomization technique, sampling with replacement, to create an empirical confidence interval for the true population correlation coefficient between two sets of quantitative data. The technique that I'm going to work with you on today does not work very well when the sample correlation between the two sets of data is less than minus 0.5 or greater than 0.5. So we need a sort of modest sample correlation coefficient for the technique we're using to be valid. I'll make an additional screencast about what we do if the sample correlation coefficient is a little bit more extreme. But here's what we do in this case. Let me compute the sample correlation coefficient between, let's say, age and abdominal circumference. This is our body measurement data from the Brigham Young study. And the correlation between age and abdominal circumference is at best modest. It's about 0.23. And we can ask ourselves the question, what is the 95% confidence interval for the true correlation between age and abdominal circumference in men? So the philosophy for this randomization procedure is the same as it's been for the entire semester. We're going to right-click on the data box and sample cases, with replacement, of course. I'll turn the animation off and replace existing cases. As usual, the number of cases we want to resample is the same as that found in the original set of data. So we have in the Brigham Young University data set 252 cases. So I'm going to change this value right here to 252. And then I'm going to impose a measure on each resample that's obtained. The measure, of course, is the correlation. In this case, it's not the mean or a sample proportion. It's the correlation of the resampled bivariate data. The formula is very simple in this case. It's just correlation, and it's between age and abdominal circumference. So for this particular resample, the sample correlation is 0.27. That'll be different each time with each resample. And now what I'm going to do, of course, is collect many measures. So this takes a little bit of time to do in Fathom. So what I'm going to do is I'm going to pause the video, the screencast, and let it collect for me 1,500 measures, and then when we get back, I'll review with you one more time how we compute the lower bound and upper bound of this confidence interval. See you in a minute. Okay, so we're back, and Fathom has now collected 1,500 sample correlation coefficients. Each one is associated to a resample from the original set of data, that is a sample taken with replacement. So we're going to do the usual things we do with this set of measures. We are going to create a picture of the associated randomization distribution. So I'm going to dump these resampled correlation coefficients in here. That distribution is not perfectly Gaussian, but it's approximately Gaussian. And it's the fact that it's approximately Gaussian that's going to let us go on ahead and get away with using the switch trick and following the usual procedure that we've had the whole semester. So what do? I plot the sample correlation, the original sample correlation from the set of data, 0.230409, and then I do what? I take and I also plot twice that value minus an upper percentile. In the case of a 95% confidence interval, that's going to be the 97.5th percentile. Okay. So I'm taking the 97.5th percentile of the measures that I collected in Fathom. I press OK. I get a lower bound right here. I'll do that one more time to get the upper bound. I take twice the original measure, and I subtract now the low percentile. That's how I get an upper bound, because the low percentile is a smaller number that I'm subtracting off. And I get this upper bound here. So we are, let's say, 95% sure that the true correlation between age and abdominal circumference amongst healthy males is somewhere between 0.12 and 0.34. That doesn't seem terribly reassuring, but it does tell us, for example, that the correlation is definitely positive. And it's true that that's a fairly wide interval, but we're going to need more data than just 252 data points if we'd like to tighten up that confidence interval. So this is how you use a randomization procedure, sampling with replacement, to obtain a confidence interval for the true correlation coefficient in Fathom.